Hi everyone, this is Yukabuka and welcome to my home on YouTube. In this video, we will continue our investigation of the keyring subsystem in the Linux kernel, and we will continue where we left off in the previous video. We were looking at the different kinds of arguments or options that can be passed into keyctl, and the next one we need to look at is keyctl setPerm, which will, as we saw in the previous episode, we know that there is a perm field inside struct key, and that is effectively the value that's being set by this function. Only bits, the available bits are permitted. I think this is a typo of some sort. It seems that only certain bits of the permissions mask is supposed to be set. If any of the other permission bits are set, it would return some kind of an error. Okay, so the next one is to describe a key. So the arguments are a key, there is a buffer and a bufflen. So this function returns a summary of the key's attributes, but not its payload data as a string in the buffers provided. So I'm guessing it returns a key's metadata. And so as a result of that, the permission would be to so there were two permissions we saw in the previous video. The first is the view and the second one is the read. So I'm guessing you need the view permission to be able to exercise this specific system call. So let's just get back to where we were. Invalidate keyctl read search link clear. Yes, this is where we were. So unless there's an error, it always returns the amount of data it could produce, even if it's too big for the buffer, but it won't copy more than requested to user space. If the buffer pointer is null, there will be no copy that takes place. Okay, so effectively it's a copy to user that happens to the specific buffer. A process must have the view permission. Yes, very good. So this is exactly what we were looking for. In order to read the metadata of a key, what you need is the view permission. If successful, a string is placed in the buffer in the following format. You have the type, UID, GID, permission, and description. Okay. So you give a serial number in, and you get a string describing the metadata of that specific key. Where type and description are strings, UID and GID are decimal, and perm is hex. A null character is included at the end of the string if the buffer is sufficiently big. This can be parsed with the following scanf. Fair enough. The next argument that can be passed in is keyctl clear. This function clears the list of keys attached to a keyring. Fair enough. So what happens if you pass in the serial number of a key instead of a keyring? I wonder what happens if you do that on this function. The calling process must have write permission on the keyring. Yes, that makes sense. And it must be a keyring. Okay, so this is exactly what I was thinking. So in that case, you will have an dir returned. This function can also be used to clear special keyrings if they are appropriately marked. This function can also be used to clear special kernel keyrings if they are appropriately marked if the user has capsys admin capability. The DNS resolver cache keyring is an example for this. So apparently there are some keyrings you can only clear if you have capsys admin capability, such as the DNS resolver cache keyring. Okay, so I'm guessing there is some kind of a capability check inside the function that implements keyctl clear. we can take a quick look at that to see if that is the case. Add key request to keyctl, and it is keyctl clear. So if I go there, we can see that this is the function. We can go to the definition of that function and see if there is some kind of a capability check at the very top. Yes, so we can see that there is a call to capable of capsysadmin, and that there is a comment saying that the root is permitted to invalidate certain special keyrings. So I guess these are some of the few functions within the keyring subsystem which actually have an SC Linux hook of some sort in it. The next one is link a key to a keyring, right? So these are, it feels like the keyctl interface is much more neat and clean when compared to add key and request key, and it seems like you can do almost anything that you do with add key and request key with the keyctl interface. There are much less unexpected side effects when using this system call. So in this case, you have a keyring serial. Okay, you have keyring serial and you have key serial, and you effectively link these two, right? So you should have the link permission on the key, and you should have the write permission on the keyring. So in this case, what it says is you must have the correct permissions. If not, if this is not a keyring, then it will return E not dir. If the keyring is full, an EN file will resolve. Okay, so I wonder if by full they are referring to the quotas that we discussed in the initial video, in the first video, or if there is a maximum capacity in terms of how many keys can be linked to from a keyring. At this point, it's unclear. The link procedure checks the nesting of keyrings and checks an E loop if it appears to be too deep, or E dead LK if the link would introduce a cycle. I see. So there is some kind of a cycle check-in involved in this. There is also a check for a maximum depth in terms of how many keyrings can be attached to one another. Any links within the keyring to keys that match the new key in terms of type and description will be discarded from the keyring as the new one is added. Right. So if there is a link from a keyring to key A, and then if we call keyctl with the keyring and key B, such that the description and the type of key A and key B are the same, then key A will be discarded and a link between the keyring and key B will be added in. Fair enough. The next one is unlink a key. You have a keyring and you have a key. It checks if there is a link in the first place. If so, it is removed. If there are somehow more links to the key, then they are ignored. So from that we can reason that there is a situation where you can somehow have more than one link from a keyring. That is not very clear to me. Perhaps it's in a case where a key is attached to a keyring and a nested keyring as well. But I'm not sure if that's the case over here. It does not seem to be the case. What they say is it looks for the first link and removes it, but subsequent links are ignored. So the question here is there a case where you can have multiple links to the same key from a keyring? And so far from the documentation, I was assuming that it's not possible. Now, if the keyring is not a keyring, you get the E not dir error value, and if the key is not present, you get E no enters the result. Fair enough. The next one is allows for searching the keyring tree for a specific key. The arguments are the keyring, the type, the description, and the destination keyring. why would you need a destination keyring here? Maybe it is to find a specific key and link it to destination keyring if present. I think that would be an optional argument. So this searches the keyring tree handed by the specified keyring until a key is found that matches the type and the description criteria. Fair enough. Each keyring is checked for keys before recursion into its children occurs. That makes sense as well. So it's like a breadth first search of some sort. Uh, the process must search the permission on the top level keyring, or else an error e-access will result. Okay, yeah, right. So we've read this in the first video. To search through the entries of a keyring, you need to have the search permission. Let's see. Only keyrings that the process had search permission on will be recursed into, and only keys and keyrings from which the process has a search permission can be matched. Right. So if you have the view permission, so I'm trying to distinguish between what it would be like to have the view permission versus the search permission. So the view permission does not have a use case wherein it allows you to iterate through a keyring and view the metadata of each key. What it allows is to search for a specific key with a serial number and view its metadata, right? So that's the difference between view and search. Search permission on a key or a keyring allows you to view all of the keys that are on the uh, key or the keyring. I think that's the difference here. So if the search succeeds, the function will attempt to link the found key into the destination keyring if one is supplied, that is a non-zero ID. All the constraints applicable to keyctl link apply in this case too. Fair enough. Errors are these specific error values, and on success the key serial is returned. Fair enough. The next one is the keyctl read, which allows to read from the payload from the key, and you also have a buffer and a bufflen. Now, if I recall from our first video, we saw something along the lines where each type has its own instantiation function, which parses the payload from user space and stores it. And when the payload is requested from user space, takes the data, takes that parsed data and somehow re-serializes it before sending it back into user space. So I'm guessing something like that it will be over here. So let's take a look. This function attempts to read the payload data from the specified key into the buffer. Right. The process must have read permission on the key to succeed. Okay, makes sense. The return data will be processed for presentation by the key type. Yes, this is what we were just talking about. A keyring will return an array of key serial T entries representing the IDs of all the keys to which it is subscribed. This doesn't make sense. I'll just try reading this once more. The returned key will be processed for presentation by the key type. That makes sense. For instance, a keyring will return an array of key serial T entries representing the ID of all the keys to which it is subscribed. Right, I see. So when you try to read the payload data of a keyring, all the keys that are part of the keyring, you get all the IDs of the keys that are part of the keyring. The user-defined key type will return its data as it is. Okay. If a key type does not implement this function, not supported will be the result. As much of the data can be fitted into the buffer will be copied into user space if the buffer pointer is not null. Right. The function will always return the amount of data available rather than the amount copied. Right. Okay. So it will copy as much as it can to the buffer, and it will return the total amount of data as opposed to the amount of data that was copied. Fair enough. So as you can see, the documentation for this subsystem is quite extensive. We're already about 3 or 4 videos in, and we've made it about halfway. And that's with skipping the SA Linux and the proc interface bits. And a large part of this document is actually the keyctl interface. So I'll probably look at a few more and then look at the rest in the next video. So the next one we have here is the keyctl instantiate, which seems to be related to the keyctl instantiate IOV as well. Let's look at the different arguments. The first one has a single payload, a payload length, and the keyring. Okay. And the second one has a key, it has an IOV. I'm guessing the length of the IOV as the IOC, and a keyring. Okay. So if the kernel calls back to user space to complete the instantiation of a key, the user space should use this call to supply data for the key before the invoked process returns, or else the key will be marked negative automatically. Right, that makes sense. So suppose process A makes a request for, let's say process A creates a key without adding the payload to it, and then process A makes the call to keyctl instantiate. And then process A tries to do a request key on the key that was just created, right, with a specific callback string. Now the kernel would execute /sbin/request key with the string that was provided by, with the call out string that was provided by process A. Now request key /sbin/request key would somehow procure or generate a key payload and then make a call to keyctl with the specific argument, the serial number, the payload, and the payload length. And as a result of that, the key would be initialized. At that point, A can return from the system call context back into user space, and either the key is initialized or it's not initialized and the key is marked as negative. Okay, so if the process must have write access on the key to be able to instantiate it, and the key must be uninstantiated. Okay. Yes, that makes sense, right? If a key ring is specified, then the key will also be linked to the keyring. However, all the constraints applying in keyctl link apply to this case too. The payload and the payload argument, the payload arguments describe the payload data. The payload IOV and IOC describe the payload data in an IOVec array instead of a single buffer. I'm sure that makes sense. So yeah, now that we're halfway through the documentation, it starts to make sense how this whole API is designed. In a lot of cases, there is an optional destination keyring to which, if provided, the found key will be linked to. Right? Okay. Now the next one is a keyctl negate and a keyctl reject. What happens here is negatively instantiate a partially constructed key. Okay, so it's not very clear to me what this is. So let's take a look at the arguments. We see that there is the serial number of the key, there is a timeout, and there is a keyring. Okay, and then again, in the case of reject, we have a key, we have a timeout, we have an error, and we have a keyring. Okay, so what this says is if the kernel calls back to user space to complete the instantiation of a key, the user space should be able to use this call to, I think it's a typo here, should be able to use this call to mark the key as negative before the invoked process returns if it is unable to fulfill the request. I see. Invoked process returns. Okay, so suppose user space, say process A tries to instantiate a key but is not able to. Process A itself is responsible for negating the key. That's what they're trying to say here. The process must have write access on the key to be able to instantiate it, and the key must be uninstantiated. Fair enough. If the keyring is specified, all the constraints, okay, this is the same thing as we saw earlier. If the key is rejected, the future searches of it will return the specified error code until the rejected key expires. Okay, so what was the rejected case? Is it the same as revoked? So I recall seeing 3 states at the very top which were related to garbage collection. One was dead, which is the case if the type was removed. The other one was revoked, in which case we explicitly revoke it from user space. And the first one was, I think, expired, right? So this, this part here, it might refer to key revocation, but I'm not entirely sure of it. So at this point, I'm going to pause this video, and we will continue our exploration in the next video. Hit like and subscribe if you enjoyed the video, and stay tuned for more.